introducing myself. My name is James Millen, and I'm a researcher at University College London. I suddenly realised, even when I was a student, the world of being a scientist in academia or anywhere is a bit baffling. So I thought I'd maybe just tell you a little bit how it worked. Right? So I did a degree in physics for 4 years. I did it at Imperial College. And then, if you want to carry on, you go and do a postgraduate degree, which is a PhD, which means at the end of that you get to call yourself a doctor, which I use only for complaining about things and making my car insurance cheaper. Oh, and if I book a flight as well. And then you're a postdoctoral researcher, which is what I am now, which means that I've got my PhD. I'm not training anymore as such. But neither do I really have any responsibilities, and I don't have to teach very much. And then if you're lucky, you then go on to get the government to give you a big chunk of money called a fellowship, or you get employed directly by a lecturer, and this is the first time you have a permanent job. So as you can see, it's actually after quite a lot of years is the first time you have a permanent contract with the university. And then if you're lucky and you do well, you get to be a professor, but not everyone does. Some people don't get to that point, even if they work. Where's my lights from? Their whole life. And also, I've been doing this position for about 4 years now. And I also do a lot of talking to the public, and I lecture at the Royal Institution on quantum theory. And yeah, so a lot of fun. But I'll talk a little bit about my research and everything now. So what I'm not going to do, they wanted me to come and talk to you after you've learned a little bit of quantum physics. And unfortunately I'm moving to Austria for 3 years by the time you'll have learned any, so I can't do that. And that's another one of the purposes of the job, getting to move around a bit. So what I'm not going to do is teach you any quantum physics. I'm going to show you what you can do with quantum physics. If it doesn't make any sense to you, that's okay. You just have to believe me that it's real and it's tested, and that we're actually using it in technology and it's useful. And really, what it boils down to is that the world of the tiny things, of atoms and photons of light, little bits of light, and single electrons, behaves in a very different way to the world around us. They do not just obey the same rules. And this is strange. So if you think about gravity, for example, right? Gravity between the sun and the earth is huge. Much bigger than the gravity between two of you sat next to each other. But you know that there is gravity there. It's just, you weigh less, so there's less effect there, but it's still there. Whereas in quantum physics, that's not really true. Things that are tiny behave in a fundamentally different way to things that are big. And so a lot of what I research is why don't we and the things around us behave in this way? Because as you learn about quantum physics and it seems strange, the only reason it seems strange is because we don't see it happening around us. Okay. So there's one experiment in quantum physics which hopefully you may get to see. Have you done diffraction of light? So where you shine light to the holes and you get this interference pattern. So that's called the double slit experiment, where you get all these things. So you shine light through two little slits. And it turns out that all of the mysteries of quantum physics are contained within this one experiment. So I'm going to completely cheat and not explain this to you, and just use this video I found to do that for me. So what happens here is we have a device which is going to fire stuff at these two little holes. And then I have a screen which is like my camera where I'm going to measure and see what happens. Okay, so if I just have some particles, some little balls, some bullets and tennis balls, and I fire them at these two slits, and something not particularly surprising happens, which is I just get a big mass of particles hitting the other end. But mainly they start off with two blobs, but then they kind of smear out. Now if I get waves like light, like the experiment you've seen, then what happens is you get interference between the waves. So the peaks of the waves go with the troughs of the waves, and then you get a flat bit, and so you get these bars where you get dark and you get light. So you saw that there are dark bars on here and there were empty bars where you don't get any wave. And that's not weird at all. It's like a water wave will do the same. So if you look at a water wave hitting a shore, sometimes the wave is high, sometimes the wave is low. There's nothing particularly strange in that, but that's not how balls, if you fire a string of balls, it doesn't happen in the same way. Now quantum physics is very strange. So in quantum physics, you fire your particle, which maybe would be an atom, or an electron, or a single piece of light, a photon. You fire them at this double slit. And you don't know what happens. Something happens. And it goes through this double slit. And then it hits your experiment at the end at this screen. But because it's, you know, a thing, it's like an atom, it's a chunk of matter, you measure it to be in one place. You don't get some kind of big smeary pattern. It's a thing, right? So it has to end up somewhere. So you fire it at this and you find it ending up somewhere. Okay? You do it one at a time and you have your experiment, you see these things go blip, blip, blip. So you do this tons and tons of times. And each time you get one particle appearing on the other side. But the really weird thing is when you do this over and over again, you get these points of light and dark again. Here. So the particles are arriving one at a time on the screen, and sometimes they're here, which is actually directly opposite the gap, in between the slits, which is where you don't really expect many particles to fall through at all, but they're definitely arriving as particles. So it's really strange, because if I'm sending one particle through at a time, well, how does it know that, for example, there are two slits there? Because if there's just one slit there, you just get a big smear of particles on the other side. But then it gets even weirder. Because what I do is I go, well, this doesn't make any sense, so I'm going to watch where this particle goes. I'm going to see which slit it goes through. So I look, it goes through that one on the left. Okay, and it ends up somewhere over here. And I watch it again, and I go, oh, it's still on the one on the left. And it ends up over there. This time it's going to be in the one on the right, okay? So I do this experiment lots and lots of times, watching where the particle goes this time, to see if anything weird is happening. And if I do that, the experiment stops working. And no longer do I get these light and dark bits. So somehow these particles that go through one at a time know whether you're watching where they're going at once. And this is one of the most tested experiments ever in physics, and it's been done with loads and loads of things. So it's absolutely true. And in fact, the way we explain this, so somehow the particle, either the particle has to know, somehow, this atom, has to know there are two slits that are there, or that one particle has to go through both of those slits at the same time. It turns out the second one is more true. So the only way this experiment can work is if that particle goes through both of those holes at the same time. So that's the bit you're going to have to trust on, that this has been tested, that actual real thing is going to be in two places at the same time. All of it, in both of the places at the same time. Until you try and look where it is, then you find it somewhere. But until that point, it has to have gone on this complicated route through two places. But we'll look at this in a little bit more detail. So there's a name for this, it's called superposition. And so it doesn't actually have to just be in science. It doesn't just have to be that it's the particles in two different places at the same time. It can be really weird things. So actually you can get particles which are spinning clockwise and spinning anti-clockwise at the same time. You can have electrical circuits where the current is going around clockwise and anti-clockwise at the same time. So it can be something that, you know, is moving at 1 meter a second and 10 meters a second at the same time. So quantum physics is full of these things called superpositions, which means two things at the same time, or many things. It doesn't have to be two things either. There's nothing special about two. It could be many, many, many things. And so the kind of state of the art with this is experiments being done where they get a neutron, right? So it's just part of the nucleus. And that can be in two places at the same time. And those two places are separated by 20 centimeters. So that means you can put your hand in the middle of this experiment, and there is a single subatomic particle going both ways around your hand at the same time. Right? It's amazing. And the biggest thing it's been done with, complicated fluorine, I believe. And so to prove it, I've got another little video here. So this is doing the double slit experiment. This is real experimental data now. Is it like just real live experimental data? And so when the molecules hit this screen at the end, they flash red. and they stay there and they glow. And so they're firing millions and millions of these molecules over and over again, these huge things, bigger than an atom, maybe about 800 atoms. And they do it over and over again. They look where these particles are hitting, and they're not just hitting in a smear. You get these light bits and dark bits. So, you know, these huge molecules have been shown to be in two places at the same time. I say huge, it's about 800 atoms big. Right? So like a full stop is 10 to the power 10 atoms or something. It would be a very tiny full stop, it's more like 10 to the 20. So, I mean, they're still very, very tiny. And that's what I talk about a bit, is why does it only really work with tiny things. So there are several ways of thinking about this. So what quantum physics is really great at is making predictions. So I can predict where those little molecules are going to hit on that screen really well. What quantum physics is very bad at doing is understanding the bit in the middle, right? I say that something's in two different places at the same time. Well, what does that mean? It doesn't really make much physical sense to us. And so people and philosophers and such like, they're always arguing over this. And there's kind of three main ways people explain this. So one, which is actually strangely like the real mainstream way of thinking about it, is in fact, until you look where something is, it's not anywhere. In fact, nothing exists until you try and measure it. And I would like to point out, this doesn't have to be people, us. It could be, you know, the air blowing against it or something. You know, it's not something fundamental about being conscious. But this is the mainstream idea, is that nothing exists. You don't know, a particle isn't anywhere until you try and look where it is, right? So it's like the old paradox of, when you can't see the moon, is it there? You know, how can you prove it is? You can't see it. Well, in that case, you can use the science. Or things can travel faster than the speed of light. So there's the idea that actually the particle knows the slits coming up. But because this experiment works with light, that means that something has to be going faster than light to warn the light that these two slits are coming. So some people believe that there's something that can go much faster than the speed of light that's always warning everything that's coming up. Or, some people's favourite, this is called many worlds theorem. Can you see the bottom line?
No.
Ah, okay, well I can read it to you. So it's the idea that actually, of course a particle doesn't go through both of those holes at the same time. That makes no sense. But actually what happens is when the particle gets to the holes, a whole universe is created where the particle goes through the right-hand hole, and the whole universe is created where the particle goes through the left-hand hole. This is called many worlds theorem, and it's very, very popular. And it's that every time any decision is made, like a whole new reality is created. And in fact, the guy who came up with this theory, he was an incredibly unhealthy man. He smoked very heavily, he drank a lot, he ate a lot of food, he was very, very unhealthy. And he did this because actually he believed in what he called quantum immortality, right? Which is that every single time there's a possibility that you die, there's always the tiniest chance you don't die. And if a new universe is created every time that happens, you're only going to be conscious of the one in which you're still alive. So it's quantum immortality. So he believed no matter what he did, he'd live forever. He died in our reality. Okay, so what I want to spend most of this talk talking about is less about quantum physics, because you'll get to learn about that. You can always go and research it. But actually what's much harder to go and research is what people do with quantum physics. Is it useful? So there's several reasons why it's incredibly useful, and the government has just started funding very, very heavily. So one very nice potential example is the possibility of building a quantum computer. Has anyone ever heard of, quantum computers ever appeared? No. Sometimes they can pop up, right? And so how it kind of, the idea behind it, and again I'm not going to go into details as to how it works, is in a normal computer, all that happens is it's billions and billions of tiny switches, transistors, and they can be on or off. And by just switching them all on and off in a certain way, that's all a computer is. But in the quantum world, of course, the switch can be on or off, or on and off at the same time. And this completely fundamentally changes how you can do quantum computation. So this allows you to solve some problems like much, much, much faster than any normal computer. So one thing you can do much faster than you can on a regular computer is you can factorize numbers. So that means if you get a number and you want to find all of the numbers, you can multiply together to make that number. And so why is that useful? So here's a graph. This is like how big your number is and how long it takes you to calculate, right? And so you can see the quantum computer is much, much faster than a classical computer. And a billion is a tiny number actually. So that's a billion is only in bits is only 30 bits, right? You think about computers nowadays. When I was a kid, Nintendo's were 64 bits, so it's already a bit ahead of that. So why is that even useful? And it turns out that creating huge numbers by multiplying two other huge numbers together is the way that nearly all of internet security works. It's very hard to work out which numbers you multiply together in the first place. You can make a code. And so all of internet security and government security is based on multiplying very large numbers together. And people who are trying to crack those codes are just trying to find which numbers you have to multiply together to do it. So in fact, a number doesn't even have to be that large until it takes like the age of the universe for a computer to crack it. So what's the record? I've got the record here. So the record number that's been broken is 768 bits long. And so standard, like your internet encryption, if you do internet banking, that's 1064-bit code. So it's getting there. The code breakers are creeping up. But that record was several supercomputers, so the whole of the American government trying to crack their code, and it took them 3 years, I think. But one of those things about the big Edward Snowden leak of all this information is that NASA are working on quantum computers very, very hard. The government's in America is putting a lot of money into breaking codes using quantum computers. Anyway, so that's one thing. But one thing which I actually think is maybe more useful is doing a search, like an internet search, right? So it turns out if I just give you a list of information, and it's the first time you've seen it, the fastest way you can look for something on that list, right? So I ask you to find orange on that list somewhere. The fastest way you can do that is you start at the first entry and then you go through one at a time, right? So Google has to do that, but it remembers the list, and then in the future it can find it faster. But in general, that's the fastest you can do. But quantum physics being weird, you can kind of search the whole list at the same time. And so quantum computers take a lot longer to search a list than a normal computer would. So that's one reason why people are very interested in quantum physics, because you can completely revolutionize computing. And there will be in, I don't know, 20 years, I'm sure there'll be quantum computers in homes. They don't do everything better than a normal computer, so you probably have both bits, but this will certainly be technology that's in your home, and when it actually exists, when it's better, because I think at the moment someone's made a quantum computer out of like 8 atoms. They're tiny, they're very basic. People will find new things to do with them. So that's the problem. No one really knows how to build one. So people have made them out of trapping individual ions, that's charged atoms. You can trap them in a vacuum and do things with them. People are working on building them out of single photons, so the tiniest bits of light, building quantum computers out of light. People are looking at trapping atoms. You can trap atoms kind of in laser beams, like this, in a lattice, and kind of build up this building out of single atoms. You can use that for doing it too. And also this rather flashy graphic came from the BBC, because some colleagues of mine at UCL managed to get a chunk of material, they got some silicon, and they managed to do some quantum computing in the actual silicon, so that's very good for technology. So this is coming up. But actually you can also buy one. You can buy a quantum computer if you want to. So they don't really announce exactly how much it costs, but it's greater than $10 million. It's the leeway. And scientists, physicists, they don't let you look at how it works, and so physicists are very unsure as to whether it's actually a quantum computer. But Google have bought one, like all the big defense companies have bought one, lots of the big governments have bought one. So they claim they've seen 1,000 times speed up over a classical computation. Okay. So that's quantum computers. So another thing, which is kind of the inverse of being able to crack codes, is you can create unbreakable codes. And this is all based around, the fact I said that as soon as you watched the particle trying to do something quantum, it broke. It didn't do anything quantum anymore. And so if you can make your code quantum, if someone tries to look at it in the wrong way, it breaks. So I've got a little graphic which comes from a talk I gave to people much older than you. There's Agnieszka and Bjorn, my two people, and what they want to do is they want to send a secret message to each other. And so what they're going to do is they're going to send it as a stream of light. And so light has a polarization, so the way that the light points. And you know, if you like get a polarizing field and rotate it in front of like a TV screen, and the screen goes light and dark, because you're kind of filtering out the polarization of light. So Agnieszka is going to get some light, and she's going to keep on changing the polarization, and that's going to be like a code of her message. So off she goes, beaming it directly into Bjorn's ear. And what's going to happen is a hacker is going to come along. He's going to try and intercept this message, right? And so here comes Agnieszka's message, and the hacker measures it on his computer. Okay? And then he sends on the message again to Bjorn, or sends on a message to Bjorn, because he doesn't want them to know he's trying to hack. Right? But then all that Agnieszka has to do is go, hey, this is my message, I want 100,100, like a digital message. And then Bjorn's will be different because this guy in the middle has tried to measure it, and that changes things in quantum physics. And so you know you're hacked. But in a more complicated way, not only can you know you're hacked for certain, you can also make it that the hacker can never read your message. So there's no way the hacker can actually read your message. They can take the message and try and read it, but it's impossible to read it. It just turns to nonsense in their hands. And this technology exists. Okay? So, for example, the Swiss, for some reason, decided to do all of their elections, their voting, via secure quantum communications. The World Cup in South Africa, for some reason, decided to transmit all the results via unbreakable codes. Beijing is digging a secure quantum channel all the way from Beijing to Shanghai. Right? I don't know how far it is, maybe 1,000 miles or something. So this is technology that actually exists, okay, and is being used to make, truly, by the rules of physics, not just hard codes, messages that are hard to decrypt, but messages that are impossible using the rules of physics to possibly decrypt. Kind of amazing. And then the final thing I'm going to not really talk about, because it's incredibly difficult to explain, is teleportation. So teleportation is real, it turns out. So light has been teleported. What do I mean by teleported? It means I have something here, and then when I wish it to, I can make it appear over here, and it does not travel through the middle. Okay? So that's what I mean by teleportation. And so, in full disclosure, it's not quite the same as taking a whole person and then beaming them somewhere else. It's like taking every piece of information you can ever have about that person, what every single atom in their body is doing, and then destroying it here and recreating it somewhere else, which to me is teleportation, teleporting the person. But of course, you get into philosophy as to whether that's truly the same person or not, even if it's identical. Or it could be, say, like swapping the colour of two people's eyes. Whereas, if I have blue eyes and if I had some over here with brown eyes, it'd be like you could instantly swap the colour of our eyes without having to send anything between. So one thing that's really useful is it's 100% perfect. So whatever you send arrives there 100% perfectly. And the record with light has been teleported 80 miles, I think. So through a mountain, it was through a mountain. So we got some light, and it vanished in one place. They didn't send it through the mountain, and it appeared on the other side of the mountain, right? And physical atom, a piece of diamond actually, was teleported 3 meters, which is not very far, but they've almost done it 3 kilometers now. I know the people who did that, so it's very close. So this is going to be very interesting when the technology is better. Question, particularly this last one, is can I be quantum? Okay, if I can do this with atoms and such like, well, can I be quantum? Can I do something quantum myself? Okay, so the question, let's start. When I was talking about superposition, I was going to be in 2 different places at the same time. So I want to say, well, where am I right now? Okay, and so if I plotted a little graph, which is where am I against how likely I am to find me, right? I mean, it's just going to be I'm here, right? You could easily see. But quantum physics says that I am in a superposition of places. And so what that means is it means that there's some fundamental uncertainty on where I would find me. Okay, so if there's an atom, maybe I could only pinpoint where that atom is to within the size of 10 atoms or something, right? Fundamentally. But, so if I went for a stroll, because it turns out it depends on your energy, then the uncertainty in where you'd find me is 10 to the minus 27 meters, which is a completely unfathomably small number. So what that actually means is if you've got me, and you just scaled everything up, right? So you've got a person, and you scale them up to be the size of the known universe, right? So this is the cosmic microwave background, the whole universe, the whole of it, all of it. The uncertainty in where I am is the size of an atom, okay? Like a single atom. So it's complete nonsense. Me, as I am now, just standing here, there is nothing quantum about me. I cannot do anything by the rules of quantum physics. It's so far outside the realm of possibility. So why is that? So one of the reasons is that when objects and things are hot, and by hot I kind of mean have a lot of energy, then you cannot see their quantum nature. And so one good trick is to make them really, really cold. So how can we make things really cold? So in a way that people often find counterintuitive, lasers are really, really great at making things cold. And I'll explain what. So okay, so what is a laser first off? So here's some normal light. And here's some laser light. And so does anyone want to be brave and just say, what differences can they see between these two? Yeah.
One goes straight.
Yeah, so there's one, it's not, yeah, it goes straight. Not only that, it goes in a thin beam and it never spreads out, or it hardly spreads out at all. So that's really important. So what that means is that we can get energy, which is in light, and you can deliver it to a very particular place. So you can focus it down into a tiny spot, you can deliver it into a certain place. Anything else?
Light diffusers.
Huh?
Light diffusers.
Yeah, so light diffusing is the same thing, it spreads out. Right? There's also the colour, right? Lasers are always some nice colour, whereas lights tend to not be quite as bright. And so one of the things is that the laser light is one colour only. And so colour, wavelength of light, is the same as its energy. So laser light has a very specific energy, not a big messy spread of energy. And so that means that certain things who only want to absorb a certain kind of energy can absorb it from laser light. And so, I mean, you can kind of see our laser here. This one, this is just a tiny video of a bit of this laser beam. I mean, you can see kind of the dust floating through it. You can see this in this very thin beam. And it's green, for example. And so the first kind of experiment was done using lasers to make things really cold were with atoms. And so the way you can think about it is light, right? You would think that just light is very difficult to exert force on something just using light. But if you think of a bus, and this is going to be our atom, coming towards us, and you throw a tennis ball at it, nothing's going to happen, okay? And so shining like a torch, a normal torch on that bus, is a bit like throwing a tennis ball at it. It's just, if you fire like thousands of tennis balls a second, really, really fast at that bus, it's going to slow down. And that's like laser light. It's bright, it goes in a beam, it's got high energy. And so, in the same way, if an atom's rushing towards you and you shine a laser beam at it, then the atom slows down. And so you can do this in a very sophisticated way. And in fact, this is a picture just using a webcam for my PhD. So this fuzzy blue blob is a cloud sitting in a vacuum, and it's glowing blue because blue laser beams are trapping it and cooling it down. And it's 5,000ths of a degree above absolute zero. Okay, so room temperature is 270 degrees above absolute zero. This is 5,000ths of a degree above absolute zero. And it's about 1 million atoms of strontium in that case. And the amazing thing is pretty much every university in the world has one of these cold atoms. And they're completely mad because you create them in an environment that's like a really great vacuum, almost as good as space. And it's many thousands of times colder than space. So how cold is space? Space is about 3 degrees above absolute zero. And these are thousands, millions, even billions of a degree above absolute zero. So they're so close to the coldest you could possibly be. They could be a millimetre in size. And there's absolutely nothing like it in nature. I always say this is the first thing that humans made that nothing like it's ever appeared in nature. It's just completely different to anything in nature. It's just manipulating matter in a completely different way. Okay, So does that mean that, is that, because it's really cold, is it quantum? Well, it can be quantum. But still, they're not very useful, because it maybe contains a few million atoms. And like I say, a full stop is 10 to the 18 atoms, okay? Not very useful, not very big. So, I want to say, can we call something bigger down? Can we get something bigger to behave by the rules of quantum physics? And then we can start putting it in technology. And so the difficulty of it is that bigger things, they tend to have more energy than little things, and they also tend to be much heavier, so they're harder to control, right? But slowing an atom down is easy because it's tiny, but slowing down something really big is hard because it's big. And also they're not as simple as atoms. The atoms are quite simple to slow down. And also, the last one here, for those who can't see it, says bigger things are harder not to watch, right? So I said if I want quantum physics to happen, you have to make sure you're not watching it. And it's very easy to not watch a single atom, or to stop any air bumping into a single atom, or anything like that. If you've got something big, it's very, very hard to stop the world watching it. So, can we do the same trick? Can we use light, like we use for atoms, to affect larger objects? There's a couple of examples which are really amazing. So one that isn't very well known is that light can actually push. Okay, so if I shine even a torch, let's say a laser beam on you, you may say, well, it's not going to push me over. But, well, if the laser beam was strong enough to push you over, it would burn a hole through you is the problem. But if you're in space, for example, and you have a big reflective sheet, the sunlight pushes against it. Not solar power, but the sunlight hits it and bounces off and pushes against it and does make it sail. And so the Japanese launched a satellite called Icarus, which they flew from the Earth to Venus. Just like you fly a boat in the wind, this was just had a big sail and flew using a sunbeam, right? So it flew on a sunbeam. Amazing. So that's light pushing, and that works because there's not very much friction in space, right? But light can also pull. So what is light? One thing light is an electric field, and so if you focus it down, you send light through a lens and you get a really bright spot. You've crammed all that electric field into a small space, and you have a lot of electric field there. And kind of very similar to with static electricity, if you charge up a rod and you can pick up bits of paper with it, right? In the same way, if you get a very intense spot of light, you can pick things up with it. So if I had, say, a little glass ball, it'll get pushed, it'll get pulled towards this. So this is a laser beam, it's being focused by a lens, so there's a bright spot here, and the thing gets pushed towards it. Pulled towards it even, and in fact then, if I was being really technical, it gets pushed up, right? Because I told you light can push, so it sits up here. So this has been done for a long time. And so I'm going to show you, I'll have to whiz through this video. This is amazing. So this is little glass balls in water, and they're being moved around using nothing but light. Okay? So people are shining little beams of light from this way into them, and picking them up, lots of little beams, and moving them around. And this is called optical tweezers. It's like a tweezer. And it's very common in technology. In fact, biologists use it a lot because you can pick up single cells and you can move them around. And you can study DNA by picking DNA up and stretching it. And so these people. And so I'm going to skip right to the end of the video, because at the end of the video they turn off the laser beam. So you can see that these little things are really trapped by the light. They're not just being pushed around, they're actually being held in place. So see, they turn off the laser beams and they all just go away into this liquid. So I really like the video because it shows. So, here in this box in front of me, I have exactly the same thing. I focus down the laser beam, in this case from two sides, it makes it even stronger. And then in the middle, so these are lenses here and here, and there's a laser beam that comes in like this and like this. Focuses down, and in the middle I can trap things. I can actually levitate objects in air. And so that's a little picture of an object levitated in air. In fact, is this this is a video, so I'll let it zoom right in on that particle. But you can see there's all this dust moving around it, which isn't trapped, but it was staying still in the middle. And so by levitating these big hot objects, there's like spheres of glass, what that means is actually we isolate them from the world. If we levitate them in the middle of a vacuum, it means that we can kind of disconnect them from anything watching. How much am I allowed to go over by? None.
Keep going.
Keep going. Okay, great. So this is really really cutting edge research. So we have an experiment just like this at UCL where we levitate glass in a laser beam and we've managed to cool it down. We haven't cooled it down very far. We've cooled it down from like room temperature to about 0 Kelvin. To 1 Kelvin, not 0 degrees, but to 1 Kelvin. So we've cooled it down by 100 degrees, 300 degrees roughly, so not too bad, but we're getting there. But what's really interesting is spheres of glass are one thing, but levitating and cooling these objects down should be possible for many things. So, for example, this is a virus. It's just about the right size and shape to do this experiment with. So here's a little picture where actually these are mirrors which you can trap light in between, and that holds a virus in the middle. And so you could try and put a virus in the realm of quantum physics, which means that a virus can be in 2 different places at the same time, and the virus is kind of alive for it. But even better, everyone's favourite, are these guys. So these are called tardigrades. So, or depending which part of the world you live in, moss piglets or water bears. So tardigrades are tiny little insects. And the thing is, tardigrades are everywhere. They're everywhere. They've been found on the top of the Himalayas. They've been found at the bottom of the ocean, right? These insects are everywhere. They're tiny, they're really tiny. You can't see them very easily with the eye. The bigger ones you can just about see. But not only are they everywhere, they also happen to be completely invincible. So they've been heated to 155 degrees C and they live. They've been cooled. No one has managed to get one cold enough, as in by putting it in a fridge or anything, to make it die. And they can survive 1,000 times more radiation than any other living thing. So they are going to be the things that are left, and everything else is gone. And even better, someone did this experiment. Someone took them to space. This is a real photo, and they survived in space. And even more amazing, what they did is they took these little insects up into space, and they split them into two groups. And one was in a box and kind of protected from the sun, because if you're in space, sunlight is incredibly strong and it would kill a human instantly, the radiation from it. But the other half of the tardigrades completely open to the sun, right? And so they brought them all in and they thought, all our tardigrades are dead. It turns out they just kind of hibernated, and half of the ones exposed to solar radiation came back alive, and all of the ones that were just in space. So in space, right, in the vacuum of space, and they survived. And then they instantly started breathing as soon as it looked like it. So these things are invincible. So the reason I tell you this is because we're not quite there technologically yet, but we should be able to levitate these guys, because they wouldn't burn in the laser beam and they wouldn't mind being in the vacuum. And then we could start trying to put those in a quantum state, which means to put them in 2 places at the same time. Right, so what does that mean? Right? So it means that we're really pushing to make normal, like real life things behave in this strange quantum way, because it will be very useful and also it's interesting to see. And this will lead to kind of really amazing new technology, as I said at the start. But now we're really thinking about doing this with living things now. So what would that mean? Okay, so if I was in 2 places at the same time, I've got a feeling that I would know about it, right? So I would hope that I would know where I am, and that should decide. That's like watching it, right? But that means that my consciousness is affected, my physical, like where I am. It'd be like being in space and then thinking really hard and being in like rocketing off through space just by thinking hard. It'd be the same to physicists. I mean, it seems very natural to say to us, like, of course I know where I am, but to a physicist it'd be as crazy as saying that. So if you got something that was like the size and shape of this insect but was not alive, and it behaved by the rules of quantum physics, and you got something that was the insect and it behaved not by the rules of quantum physics, then you would be able to say that consciousness and quantum physics cannot exist together. But if it does work, it means that you could teleport these guys and all this kind of thing. And with that, I'm going to finish. So thank you.